is just a low-pass filter that attenuates your signal, and the ones that we have been looking at are left-hand plane poles, and that's because they are of the form 1 plus s over omega, and that means s is less than 0. So to make this term right here become 0, you need s to be negative here. And if you think of a number line, then s is going to be to the left of a 0, and that's why it's called a left-hand plane pole. And the only problem that left-hand plane poles cause is attenuation in your signal. You'll see right-hand plane stuff that messes up feedback circuits, but left-hand plane poles, they just attenuate your amplification. Okay, and though we haven't talked about it much, as a pole is hit, there's a delay through your circuit and you get a phase change. So your output is not necessarily in sync with your input. And I'm sure you've seen that in your lab. Okay, our method, okay. Then on to zeros. 0 is something that makes the numerator 0. And you can see right here you have S times the gate drain overlap minus GM. And what's interesting there is now S is a positive value. So to make the numerator 0, S has to be a positive value. That means it's to the right of 0 on the number line, which means it's a right-hand plane 0, which means it's not good with feedback. Okay, this 0 right here is due to that capacitance from the output to the input, specifically the CGDO, the overlap capacitance. And I think that's for this slide. Okay, and this is just a comment on it being a right-hand plane 0. Let's make that a right-hand plane 0. Okay, let's see what else. As mentioned, the phase, as your frequency starts to go up, your input can get out of phase with your output. And again, we'll be looking at that on Monday a little more. But just in general, with a pole, what you see is that there is a 90-degree change in phase at each pole. Okay, and 45 degrees of that change happens before your corner frequency, and 45 degrees of it happens after your frequency. So right at your frequency, you've dropped 45 degrees. And it starts to change whatever your corner frequency is divided by 10. So FC over 10 is where it starts to drop, and then 10 FC, in other words, 10 times your corner frequency, that's where it starts to flatten out again. And that happens as many times as there are poles. Okay, and this isn't, sorry about the debugging going on here. A 0 is created. A 0 causes to increase with frequency. Okay, so as a pole made the magnitude drop and the phase drop, a 0 causes the amplitude to increase. And the phase, it increases if it's a left-hand plane 0, but we had a right-hand plane 0, so it actually decreases your phase, which you'll see is a bad thing. There's a couple of special cases. There's a pole and 0 at the same frequency, and what that does is basically cancels each other out in the ideal case. On a simulator, unless you do Monte Carlo or something like that, they'll just cancel each other out if you have them at the same frequency. They can be seen, they can be caused by, you know how they had kind of the one side of your differential pair diode connected, and you use that to as a gate voltage or a base voltage on the other branch of your differential pair that can cause a pole zero doublet, and it can mess with settling time. So amount of time it takes until you actually get to your result. Okay, there's also complex poles and zeros, and we'll talk about that a little bit more on Monday. But when you get an equation like this, notice in the bottom you have an s squared and then an s and then a constant. That's a quadratic equation. You can solve the quadratic equation using the solve a quadratic function as using the quadratic equation, and you can get a complex solution. That still is used, and when you plot it, instead of plotting it just across the frequency, a line representing frequency, now you can have poles and zeros that are off the x-axis, and consider the y-axis as the imaginary axis and the x-axis as the real axis, and those can be plotted, and that's perfectly okay. These are three complex pairs. Okay, this is just a summary of if you have a pole, this is what happens to your Bode plot. If you have a zero, this is what happens to your Bode plot. And these are actually left-hand plane poles and zeros. Okay. Yeah, these are all left-hand poles and zeros. This is just a summary of what happens. For example, a zero increases your magnitude from wherever that zero occurs. You increase your magnitude, and it also raises your phase. Okay, for a real pole, your pole drops your magnitude and drops your phase. Okay, and a constant. Remember when we had the amplifier, where we had those two amplifiers chained together, cascaded. The gain of those amplifiers turns out, since it's those two, the amplification is multiplying the rest of your equation. You can pull those out. When you take the log of that, it becomes a separate term in your log equation. That becomes a constant. So those gains, that A1 times A2, that's an example of a constant. And that's a value that's always exists. Everything else is added to that. Okay, the other thing that you can have, again, that right-hand plane unstable zero, right-hand plane unstable pole. I believe, I'm going to check this one more time, but I believe that the zero just acts like a pole, and the pole just acts like a zero. Okay, and what can happen if you have those right-hand plane, what is this? Right-hand plane zero, it can give you oscillations where you think you should just have a flat value on your output. Instead, it'll oscillate.